The title of our work is Natural Climate Reconstruction in the Stave Churches through time series processing with variational autoencoders. In this presentation, we firstly spend a couple of words talking about Stave Churches, and then we will move talking about the dataset we had and the choices we made about it. We will then present variational autoencoders and the particular implementation we exploited for our purposes. Finally, we will talk about results we got and conclusions. Stave churches are medieval wooden church buildings, once very common in Northern Europe. Nowadays, they are both tourism destinations and they also host religious events. But because of this, heating is turned on and off many times during a year, especially during cold seasons. This is of course threatening the delicate structure of those buildings that therefore have to be preserved. It would be very useful to determine what the historical natural climate of those buildings would be in absence of human interventions. The goal of our project was to start from a temperature time series spoiled by the action of heating, clean it up, and obtain something that resembles what a natural time series would have been. The dataset covers 1 year, and it is made of temperature and relative humidity records taken every 5 minutes by 3 different sensors. The L1 and the L2 record the internal climate of the church, whereas the L3 is placed outside. We also have a metadata file which tells us when the heating was turned on and off. If we think to plot the internal temperature versus the external one, we get something that resembles an ellipse. Notice that, however, those points that, according to metadata, belong to the heating events lay outside this ellipse. This will be useful in the following in order to determine a score for the models.
The main thing to consider in order to successfully train a variational autoencoder is the amount of data. In our case, we have only 1 year of recording in which some months are completely useless due to the heating. Obviously, we don't have more data for the internal temperature of the church, and it's more probable that we could find an online free dataset for the external temperature, based on the usual weather forecast. So the idea is to find a way to get data for the internal temperature given only the external one. Indeed, we believe that the internal temperature follows the external one in an attenuated and delayed way. This is a well-known concept in construction engineering related to the thermal inertia of the building. The dataset that we found online is provided by a station located 5.3 kilometers away from Ringebu at the same height above sea level. It has 5 years of measurement, so we hope that now the variational autoencoder could catch the periodicity of the year, otherwise impossible with the Ringebu dataset. The day and night and seasonal cycles are the two main responsible for the temperature change, so our variational autoencoder must absolutely catch and learn them. So, from an engineering point of view, we are figuring out what could be the transfer function of the walls of the church. This is much more naive compared to solve numerically the three-dimensional heat partial differential equation, but is however a method developed and used by Ashray that can be found in the literature. In our case, we have used the simplest case in which the transfer function has a zero-pole structure plus an eventual static gain. This structure gives us the possibility to have a finite attenuation at high frequency that is a trade-off between consider the effect of the small fluctuation of the external temperature and cut them completely. Here below we can see the MATLAB Simulink circuit devoted to tune tau1, tau2, and k. In order to reconstruct the internal time series, we proceed as follows. At the beginning, we tune the parameter of GDS, and to do so we use the Ringebu dataset limited only to the warm season, meaning spring and summer. The evaluation of the best parameter is just done with a grid search with a L2 loss between the real temperature, internal temperature, and the reconstructed one. Then we apply the external time series of the station to the tune transfer function, and we rebuilt the augmented time series of the internal temperature. As we can see in the figure, the previous peaks due to the heat are now disappeared, and so we can hope that the device can successfully learn the natural climate of the church. The training set will be composed by the external time series from the station, meaning the analogs of the sensor DL3, and the synthetic reconstructed time series, here in blue, the analogs to the sensor DL1. We want to finally remark that our final estimation of the natural climate of the church is not the time series reconstructed by the GDOS. This is just an original way to augment data and provide a good dataset to the variational autoencoder.
Variational autoencoders are machine learning methods based upon Bayesian inference. They model the posterior as the distribution of the latent variable z, which is inferred from the observed data, through neural networks. These neural networks are trained with a loss function that takes into account both a reconstruction term, which is the All-2 loss, and the Bayesian term of regularization, which is the Kullback-Leibler divergence, weighted by a coefficient beta. In this slide, we can see the various elements of the variational autoencoder. We give in input a time series sample. It is encoded through a neural network. Then the reparameterization trick takes place in the bottleneck of the model. So the sample is mapped to a point in the latent space, which is finally decoded as a new sample with the same dimensions as the input. For the architecture of the neural network, we exploited the characteristics of our dataset. These are the key choices we made. First of all, in order to find periodic patterns, we implemented a couple of convolutional one-dimensional layers. Both of them have a meaningful kernel size of a day or half a day. For regularization, we added a dropout layer. Then, a long short-term memory layer was placed to take into account long-term correlations of the time series. Due to the complexity of the problem, we needed a high number of latent dimensions, such as 17. And we also fine-tuned the beta coefficient of the loss. For the decoder, similar choices were made, except that the convolutional one-dimensional transpose layers were implemented due to the need of upsampling to go back to the original dimension. To build our training set, we subdivided the long time series into week-long samples with stride of a day, and for each of them we fed the neural network with 8 standardized variables. 4 are from the detectors, so we have internal and external humidity and temperature, and 4 are auxiliary variables that encode the time coordinates, so we have the cosine and the sine of both day and year. Now onto the results. Here in light blue, we see the reconstruction of this training sample. The relevant features are all successfully filtered and denoised, and the daily periodicity is almost perfectly encoded. You can take a look at the latent variable distribution by plotting the scatter plots for each dimension of the training sample's encodings. We mainly find clusters of winter days in blue, green and purple days, which are autumn and spring, and finally in red we see summer days. So the yearly pattern is successfully recognized and learned by the variational autoencoder.
As conclusion for our work, we would like to present some methods to detect when the internal temperature is too different from the historical climate of the church. A first possibility is to use the thermal ellipse described before in order to generate a quantitative score that allows us to detect points which are not compatible with the thermal inertial effect that parameterize the wall response. In order to do this, we applied the logarithm to the multinomial function fitted on the ellipse. What we obtain is this score, called Gaussian score, which gives a really small penalization, almost null, to the points inside the ellipse, while the points outside the ellipse receive a larger penalization as they get further and further from the ellipse. As regards the variation of the encoders, we have that in general this method can be used to generate the historical climate of any church. That is, if we have enough data to train it correctly. If the amount of records is large enough, 30 years as an example, we could also avoid using the data augmentation procedure. Comparing the recorded internal temperature with the reconstructed one, we can see that if the recorded temperature exceeds too much the generated one, then it is a good idea to evaluate if it's necessary to turn off the heating in order to preserve the church structure. If we are interested in generating a possible natural temperature related to a particular period of the year without providing any input to the neural network, we could use a specific tool of DeVal, the latent space sampling. It consists in generating brand new data, decoding particular points sampled from the latent space. In order to do this, it is necessary to understand which region of the latent space corresponds to the desired year period. In our implementation, this is a very difficult task, because we often use high-dimensionality latent space, from which it is very difficult to recognize the region of interest. Surely, this could be improved in further works. Thank you for the attention, and we hope that our work will be useful.